just making sure that it works. Yeah. Okay, perfect. Testing, testing. Okay, awesome. Mhm. Yeah, I do remember that. Yeah. That's like, yeah. Yep. Okay, awesome. Thank you, Jim. Yeah, so I am going to talk to you about all of those things. Not quite all of those things that Jim just mentioned, but this is my like hodgepodge title that lets me submit a title in abstract without having decided what I'm actually going to talk about until I actually get there. So yeah, my group, this is sort of what Jim was alluding to, but just like the brief primer before I dive into some of the results. But my group really at Toronto does a wide variety of things. Maybe we've branched out too far and need to rein it back in a little bit, but we really do things on new regimes of astronomy, but also stellar astrophysics, what we can from that. And then we are involved in the multi-messenger gravitational wave astrophysics. And we like to use observations across the entire electromagnetic spectrum. And again, using both stellar exploration and stellar populations to try and learn about and eventually die and influence the rest of the things around them. So that's a lot. I'm not going to talk about every aspect of that, but just to reiterate, again, not that people in this room need this, but a lot of this stuff we've been doing really has been revolutionized in the past decade by large numbers of wide field surveys. Obviously, on the time domain side, we're now in this era where the community is discovering 20,000 some explosive transients every year, studied to various degrees, but we're no longer just in a numbers game. It's actually constructing your experiments to do the science you want when there's just a plethora of data. And then similarly on the side, you know, Gaia astrometry plus all sky surveys, like give us an unprecedented view of billions of stars, and including now on the time domain on the stellar side as well, really has revolutionized things. So with that, I am going to just give you sort of a highlight of a bunch of recent results and things that I think are interesting on many of these fronts. This is my alternative like outline of my talk. So what this is, for those of you less familiar, is, this is an example of one of the binary sort of evolution pathways that you might take if you wanted to eventually make a neutron star merger that something like LIGO, Virgo Quadro would eventually see. And the biggest thing I want you to take from this is it's complicated. There's a lot of stuff going on. You start with two stars, you have a mass transfer, one of them explodes, you need to survive that. Then you go on, you have further mass transfer, you have something called a common envelope phase where one star engulfs the other, you need to survive that. Then you need to survive another supernova, and then eventually you might merge. And so the biggest takeaway here is this is a complicated process. This is part of why they're rare. There aren't a lot of neutron star mergers, a lot of binaries that survive this. But the other takeaway is there's a lot of steps in here that you should flag as maybe we don't understand this so well, or there's lots of uncertainties. There are many places where we could learn more. So what I want to use this, again, it's not quite an outline, but this is sort of a framing for the type of work that we do. So I'm going to use this and sort of step throughout my talk, using it to highlight there are a couple different phases of things that my group has been working on recently where we're trying to understand different steps in this process a little bit better, again, to sort of more holistically understand how do stars evolve, how do they die, what are their ultimate fates. So we're going to try and we'll see if we make it through. If we don't, that's what's nice about a modular talk. I'll cut one of these, but we're going to try and talk about a few different of these phases and sort of tidbits of results along the way. So if we zoom in and actually just start off with the idea of a supernova explosion, and particularly in this case, this would be an example of a supernova that probably was a star that via binary interaction had part of its hydrogen envelope removed and then exploded as a hydrogen poor supernova. But we're going to use this as a frame. What are some of the things we're trying to learn about the supernova still? Obviously, these are the big questions. We're trying to learn what are the progenitors to core collapse supernova, what's their final structure and behavior, and also what's the explosion mechanism and the final compact objects left behind. Some of this you might think are things that have been, well, they have been studied for a while, but are still things that we don't fully understand. For example, on the supernova progenitor side, we do know some things about what stars explode. We look to nearby galaxies. We sometimes have pre-explosion images, and you see red supergiants that explode as supernova. So we do have pictures like that, but also from a number of our studies, again, looking at these pre-explosion images, you also have things like progenitors that have been found that you maybe didn't expect. Things like yellow supergiants exploding, which you wouldn't predict from single star evolution. A lack of progenitors you might have expected. For instance, we think again from the single star perspective, this is a theme, but you might expect that massive Wolf-Rayet stars explode. We don't see those when they look nearby. And then instead, they'll point to classes of stars that, you know, probably exist, but we haven't seen before. So there are a lot of open questions in this field. On the sort of explosion mechanism perspective and what are the compact objects that are produced, the main things I want to highlight from this in terms of some of the uncertainties that we have going to this observationally is first, in terms of what compact objects do different types of stars make when they explode. There's sort of this textbook picture where up to a certain mass, you make a neutron star, then you start making black holes. This is not the case. There's a lot of debate about where this is, but this is just one example of a plot where now in more modern explosion simulations, you have what are called these islands of stability, where maybe you make neutron stars, then you make black holes, and you go back to making neutron stars. And exactly where those boundaries are very sensitive to what the final structure of your star is. So again, the entire evolution it underwent before is totally going to dictate what your final outcome is. And similarly, just in terms of the explosions, we do know that some supernova have jets that are emitted. We see them as gamma ray bursts. That is quite clear. This is just a plot from, it's a combination of radio, X-ray, and other data where the squares are sort of the amount of energy in the bulk ejecta from a supernova. And then the circles are the amount of energy in sort of the fastest moving ejecta. And you can sort of get a profile here. The GRBs are up here in blue, so they have a lot of energy out in this material moving very fast. It's a little less clear as you sort of get to more standard supernova. Are there still similar things? Are there central engines that are contributing to those explosions as well? Or is it really like a dichotomy and not, how does that continuum or dichotomy work in terms of how the explosions are actually triggered? So again, there's a lot of open questions. I want to tell you some recent things we've been learning on trying to dive into some of these questions. And particularly, I'm going to focus on, if I had to pick something, hydrogen 4 core collapse supernovae. These are the ones, again, it's a core collapse of a massive star, but ones that somehow had hydrogen removed before they actually exploded. We know a lot about these systems already. For example, I'm showing you two results here from different work where we know, for example, they have relatively low ejecta masses, on average only like 1 or 2 to 4 solar masses of materials thrown out. We also know they make up something like 30% of all of the core collapse supernova. And both of those things together point you towards, it's not your massive Wolf-Rayet stars that are exploding, but rather lower mass systems that would have had to have their hydrogen removed via binaries. We know that pretty firmly, like binaries have to play an important role in producing these supernovae we see. But there are still a number of interesting things that I think are not fully resolved here, or we still need to explain based on recent results. So some of this is, okay, we think they're coming from binaries. That's pretty clear. But the naive thing to say then would be that you might actually have your hydrogen-rich supernova and your hydrogen-poor ones are mostly coming from the same mass stars. And the only question is, did they have their hydrogen envelope removed or not? But when we actually look in detail at the populations, there are a few notable differences between your hydrogen-rich and your hydrogen-poor supernova. One that I'll highlight here is that now as we are actually going through populations and have larger samples of them, if you look at, for example, how much radioactive nickel is produced in the explosion, that triggers a lot of the light curve you see. And the main things to point out here is the green line is sort of the distribution of that you find for hydrogen-rich supernova. So again, imagine red supergiants exploding. And the other two lines are two different studies, different methods, but similar distributions for these hydrogen-poor ones. So again, there's some uncertainty here, but the biggest thing you should take away is that these are other. It does seem like these hydrogen-poor ones are producing more nickel on average than the other. So what could be causing this? One obvious thing is it's an observational bias, that we just aren't seeing the low nickel mass examples of things that don't have a big hydrogen envelope around also contribute. This is almost certainly part of it. You do expect the ones with really low nickel masses to be quite faint. And so again, they're the hardest ones to find. But, you know, I don't know if it's enough to skew this whole distribution. I think some of the ZTF volume limit samples might help answer this a bit, but you need to skew that distribution pretty hard to make these consistent with each other. So it might be that there is actually some physical effects that are leading to this as well. A couple of things are, you know, maybe there is still like a mass contribution to this. The amount of radioactive nickel you make isn't 1-to-1 with your core mass, but is related to that. So like one way to think of this is there are more high mass progenitors fractionally for these hydrogen poor events. And so maybe we're seeing things like maybe your binary fractions or distributions are mass dependent. And so you're seeing the effects of it on these distributions. Or that'd be an indication that, you know, you shouldn't just think of these stars as you take the same initial mass star, one you take the hydrogen envelope off, one you don't, and then the cores are basically the same when they explode. That almost certainly isn't true. Probably the binary stripping affects the structure of the star, and then that propagates down to what its final core structure is, and therefore what type of explosion it makes. And these are things people are trying to dig into now to understand, do we truly understand how these explosions are working and what the populations are? And I'll just mention this isn't limited, like the nickel mass is some of the most recent results people have been focusing on and how it's different between populations, but it's been known for a while that there are distinct differences that we see. This is another example where instead you're looking at environments where these stars are actually exploding. So again, local environments, you can do things like for very nearby supernova, you can ask, here's where the supernova went out. How close am I to the nearest H2 region or star forming region? Am I close on average, farther away? This is a plot that, you know, don't worry too much about this axis here. Mostly it's telling you a bit like how correlated are these supernova types with the star formation in their host. And the biggest takeaway you should have from this is that, you know, the hydrogen poor events, which are some of the colored ones here, are very correlated with the star formation, whereas the hydrogen rich ones are less correlated with them. So the sort of zero sort of way to interpret this is you do have younger ages and therefore higher masses for populations. So again, saying they're not just equal populations that we're looking at. There is another effect dictating it besides just was its hydrogen envelope removed. And we're still trying to piece together from the binary population side if all of this makes sense. The other thing I want to highlight in terms of trying to understand how these stars explode and what are their progenitors actually is that when we recently have been looking more carefully at this population of supernova, it looks like there's extra energy coming from somewhere. So usually when we look at the light curves of a supernova of this type, here's an example, they go up for a few weeks, then they fade a little bit, and they sort of then have a slower decline for a few months after that. Usually how we interpret these light curves in this case is that what you are being powered by, where that emission coming from, is radioactive decay. So again, you synthesize this radioactive nickel in the explosion, you have an initial rise as it's diffusing out through the ejecta, and then you decline from there. What's interesting though is that when you actually go through and did this, and a number of people using slightly independent techniques found that when you do this, and especially for a sample where you actually follow to late enough times to get this sort of late time decline is related to the radioactive decay. When you do that, you actually find that it looks like observations on average for a given amount of radioactive material produced are more luminous than you would expect from our current suite of theoretical models. So here what you can see is the blue dots observations. This is peak luminosity, and this is the amount of nickel we infer made in this explosion. And the biggest thing you should take away is the blue dots are all higher than all the other colored points, which are theoretical, like how luminous should you be at maximum for a given amount of nickel produced. So there are ways to like adjust this a little bit, but it looks like something else. And again, a number of groups have done this using various different modeling techniques and have all found the same result. That it looks like, you know, object by object, something like, you know, 7 to almost half of the light at maximum might be coming from something besides radioactive decay. The question then is, what is that? And what does that tell us about the explosion? There's sort of two obvious culprits. Different people have advocated for different things. one obvious thing supernova people like to do is say maybe there was a magnetar produced, and that's something that can give you some extra energy. This was the interpretation that was favored by this recent paper by Rodriguez, Udinakar, and Danny Pouts. They favored that you are creating magnetars that just produce some extra energy that contributes at those early times, which then tells you something about what kind of compact object you are making in these explosions, what the spins are, things like that. The other possible interpretation you could have for this is that another way you can get extra emission from supernova is if you have, when your star explodes, if you have a slightly puffed up envelope, so it's out further, when the shockwave blasts through it, you will heat up that envelope and it will cool and produce some extra emission. There was actually a few models that were done by Io Pfizer, some with Jim a few years ago, where they actually, like this, where you had a more puffed up progenitor to these things. And those are actually the main models we could find that reproduce what we're seeing for how bright these things are versus how much nickel they make. They actually match very well with a lot of the observations. So that would be another possible explanation. We do know there are examples of some hydrogen poor supernova that show other evidence in like their UV light curves of having sort of inflated envelopes around them. There's also some evidence for this from progenitor detections. There's only a handful of these hydrogen poor supernovae that have progenitor detections, but one of them is sort of what I would consider anomalously sort of cool and inflated compared to what we expect from the stellar evolution perspective from here. So this is looking like, again, I don't know what the answer is for where this extra emission is coming from. A number of groups have found it. It does seem like it could be something to do with a central compact object, or it might be that the structure or environment around these stars is different than sort of our standard picture, and that is leading to some extra emission in the light we see. Either one would be very interesting, either from the compact object structure, or how does that final evolution progress for some of these stars. So, and I'll just add, like sort of ending there, that this isn't unique to these hydrogen poor events. This is something a number of people here, including Wynn, have worked on, that, you know, this has been something that has been found for many, many types of supernova as our data gets better. They are leading somewhat dynamic lives during their final years. It's not that unusual. People are still working on the statistics, but to find things on like things that are inflated before they explode, again, indicating that something is going on with the star, either due to sort of interaction with companions or the star itself undergoing changes in its life at the end, which all are going to propagate through to what type of compact object it will create and explode. So that was sort of a highlight of some supernova work that we've been doing recently and trying to understand those populations. Let's shift gears within this diagram and sort of hit on some of the stellar work before swinging back to transients at the end of the talk. So the two phases that I'm highlighting for you here are phases in this evolution where you expect to have a binary of which at least one star is what we're calling a helium star. So those are stars that, again, have had their hydrogen envelope stripped off, and then you're viewing as a hot helium star. So this is where we think they are. Star had its hydrogen envelope moved. This is what it said. This can happen a couple of different ways through binary reaction, either through some sort of stable Roche-Loeb overflow or via common envelope. And there are a number of ways you can remove this, but there are a couple different processes for making these hot helium stars. We think they're really important for a bunch of evolutionary processes. Again, binary evolution, when you look at binary population statistics, this should be common. Something like a third of massive stars are expected to have their envelope stripped in this way. As I just said, we think these types of binaries are what are leading to hydrogen poor collapse supernovae from things like their ejecta masses. We think it's important if you want to make a neutron star merger, you need these. I'm just giving you a laundry list of reasons you should care. Hopefully you do. If you care about stellar populations, you should care about these objects. They are things that you strip the hydrogen envelope. They are very hot. They emit most of their light in the extreme ultraviolet for most of their lives. But they have longer lifetimes than things like very young, hot, massive stars. And so it does actually matter in terms of, if you want to look at integrated light from stellar populations, you can get extra UV light at later timescales after a starburst when you start to incorporate these binary products. But it really matters how you treat the binary evolution, how many should there be, exactly how many ionizing photons get out. You would love to have observed populations of these to tell. Unfortunately, despite their importance, until very recently, there was like one object that was known that was a helium star kind of in the mass range that I'm talking about here for things that might eventually explode and make neutron stars. But this was almost certainly an observational bias. Some of you have seen me talk about this before, so I'll do the first intro here quickly and then tell you where we're going with it. One way to try and find these objects is, again, these stars emit most of their light in the extreme UV. So the idea is once you have more UV, you can start to hopefully find these stars by looking for things with UV excess. So what we did was we took this beautiful data set that had been taken by the Swift UVOT instrument back like almost 10 years. They did mosaics of the Magellanic Clouds. They did a number of good pieces of work with it, but there was no like catalog of just photometry of all the stars. So we went through and like it was actually a very difficult process to deal with in terms of it was the best data set there was, but you still do have to deal with crowding. So we did photometry on about basically 500,000 sources in the two clouds, and then started looking for things that had excess UV light. And we found a bunch of things, and sure enough, you start finding things that pop out in this region. And when you start taking spectra of some of these objects, so here is a UV versus UV minus optical color magnitude diagram. The big clump here, that's the ZAM. That's like main sequence stars. Anything over on the left here are things that have extra UV light compared to what you'd expect. And those are candidates where you have a second component there that's contributing extra light. And when you go through and actually start taking spectra of these things, you find that you are seeing helium stars. So here's just a montage of some of the types of observed spectra we were seeing in that region. So the top one is something that actually just looks like a very hot star. If you don't look at spectra of stars, don't worry too much, but basically you see helium-2, which means there's something hot there. But this is way too faint to just be an O-type main sequence star. And instead, you know, it's a very hot star. That's the main thing you're seeing. Spectra on the bottom, you see these big Balmer lines. That just looks like a normal B-type spectrum. And the one in the middle is sort of a composite between them. You see the Balmer lines, but you also see the helium-2. This is what you expect when you start taking main sequence stars and helium stars and adding them up in different ratios of their flux contribution. So we went through and like you actually find, and you can do an assessment and actually look at these, and they have similar temperatures, luminosities, and compositions to these stripped helium stars we're looking for. They are hydrogen 4, all the way to sort of 0 hydrogen content to maybe, you know, 30% hydrogen by mass on their surface. So these are hydrogen 4 stars, and they are falling right in the temperature and luminosity range you expect for stars that were initially sort of 8 to 20 solar mass stars that have been stripped of their hydrogen. So we recently published that we had found these. And again, previously there had been one example of these. This was a sample of some 20 objects that we published. But now we're trying to do fun stuff with these. So I wanted to give you a little highlight of some of what we are doing now with this population of stars, which again, the idea was we listed all these things that they're important for. We showed that they do exist. Obviously, it would have been a massive problem for like binary population census people if we found none of these stars, because that would mean something was horribly wrong. We found them, so that's nice and reassuring, but what other science can we do with them? So just a few things to highlight, the things you should see coming out somewhat soon. One is that some of the objects we found, and in retrospect, this is because this is what we have the highest efficiency to find, but some of these objects show evidence for having compact object companions. So again, these are ones like sort of this top row where I showed you here, where in our optical spectra, it just looks like a helium star. We do not see any evidence in its spectrum for a main sequence companion or anything like that. It just looks like a helium star, but it has like a luminosity indicating it originally came from a lower mass companion. So it's possible these could have been truly isolated stars or something like that, something that was picked out in a binary, but we've been following these for a while. Obviously, ways to address these and to also disentangle, is it just a low mass main sequence companion, or is it actually a compact object like a neutron star, black hole, white dwarf? Because you could, for instance, hide, like, it wouldn't be impossible if you just had a 1 solar mass main sequence star, maybe you wouldn't see evidence of it in the spectra. But we're sort of going through and actually getting orbital solutions, disentangling, looking for X-ray emission to see, are some of these actually this phase where you have a strip star with a compact object companion? One example of this, one of the objects in our original study is one that we have now gotten an orbital solution for. This is the radial velocity curve. It has a 4.2-hour orbit. And it's one such that you take that plus the mass of the helium star we have, you cannot fit a main sequence companion inside that orbit. Like there is 0 way it would fit. It has to be a compact object of some kind. The minimum mass for this compact object is like 1.2 solar masses. So it might be a white dwarf. It would be a very high mass white dwarf. Otherwise, it's a neutron star or potentially a black hole as well. We're still disentangling this a little bit with those options. You know, you also have a beautiful, okay, I think it's beautiful, like where you see ellipsoidal modulation, sort of confirming that this is there. This is a 19th magnitude star. It's hard to get this white curve. But it really does look, this has to have a compact object. We also do have X-rays for this one, although I'm not showing it here. And it is one that it really does look, it's tight, that it's something like sort of this phase in the evolution, where it's something that, you know, and we're sort of trying now to do some more detailed modeling of this probably will undergo one more interaction phase in the future, but modulo some of our understanding of that, this is a system that's tight enough now that if it survives the second supernova, it should eventually merge as a compact object merger. And that's just one example of these objects that, again, seem to have compact object companions, which, again, we're very sensitive to because they are going to be the bluest objects in your sample. If you only have the helium star, you're going to be incredibly UV bright. As you start to add main sequence stars in, you move back closer towards the main sequence. So in retrospect, we are very sensitive to this particular type of binary with our type of study. And we're working now on sort of the full set of these objects. This is just some preliminary results of showing you the diversity of the systems that we're actually seeing here. So this is a range of periods we're finding. This is the 4-hour orbit one that you see here. You know, we do have a couple of other ones, and this isn't fully complete. We have a few more orbits besides these, but there are a few less than 1 day, but they go all the way out to about a year in terms of orbits that we're seeing for these systems that probably have mostly compact object companions. So the second thing that we can do with these populations is actually try to understand the mass loss from these stars. So again, there had only been one example of this type of star in this mass range until recently. So mostly people assumed their mass loss rates would be extrapolations of like higher luminosity Wolf-Rayet stars. You can see the winds are much weaker for these. So what I'm showing on the left is this is a compilation of helium stars of various masses. So the top is sort of your high mass Wolf-Rayet stars, so you get these big emission features that are due to the strong winds being blown off of these stars. And you can sort of see a progression down. All of the top three are examples of Wolf-Rayet stars in the Milky Way or the Magellanic Clouds. And then all the way at the bottom here, these are examples of subdwarfs that are known in the Milky Way as well. Our stars sort of bridge in between those in terms of their mass. And you can see they basically, except for a couple little sort of ionization and nitrogen lines, they're mostly absorption features. And the biggest thing to take away from this is when you put limits on their mass loss rates. Again, if you don't have wind features, you can only really put limits on it, but they're very low. We can constrain them to be less than like 10 to the -9 in some cases. And this is, again, much lower than you would expect for some extrapolation. Some of these like sort of colored lines here are what you would do if you extrapolated Wolf-Rayet winds. So it's not unexpected that as you go to lower luminosity, you might fall off at a certain point as you fall below a certain like Eddington factor, but it does seem like they're very low. And this really matters. Not only do your wind parameters affect your final surface composition, so like what supernova you'll explode as, they also affect the radii of your strip stars. So they're going to affect which ones of them will undergo subsequent interactions that might be necessary for mergers. And also, if you, again, cared about the starlight from these, how strong their winds are affects the amount of ionizing radiation that can actually escape because you absorb that material. So if you want to recreate sort of the light from your JWST, like high Z galaxies, you care not only about including these stars, but also what their winds are, because that's going to affect. On the supernova side, one thing to just note is that there is actually a disconnect now between the types of mass loss rates we're measuring for these and the types of mass loss rates you get when you look at radio emission from supernova. So radio emission from supernova can trace like the shock front basically going through material that was around your star before it exploded, and it can give you constraints on what the wind was. And okay, there are degeneracies in this. So maybe I want to actually explain this whole plot for time's sake. But the main thing I will tell you is that most hydrogen bohr core collapse supernova seem consistent with pre-explosion mass loss rates more on the order of like 10 to the -6 solar mass per year or higher. Whereas for these stars, we were finding, you know, some of our high luminosity ones, we were like at 10 to the -7, but it goes down from there. So this maybe isn't unexpected. We think most of these are in core helium burning right now. So they will undergo later evolutionary phases, but this is indicating probably you need a change in mass loss behavior, again, shortly before explosion to get these things to actually up together with one another. So there are interesting things to think about here of whether you actually can make our supernova if their winds are so much lower. And just highlighting, we do have HST spectra in hand for 10 of these that, hopefully we can actually measure the mass loss rates now. So that will be coming out shortly in terms of actually what better prescriptions to use might be. And then finally, the thing I'll mention is, so far we've published like 20 objects. The original UV catalog I mentioned, here is an example. This should say Ludwig et al. 2024. Our original catalog of UV sources, we have several hundred candidates in the Magellanic Clouds. And we have been, you'd love to do rates with this. This is something we're going to be working on. And we have been getting with AAT in Australia, we have spectra now of about 1,000 of these in hand. And some of them look exactly like the ones we found already, but like a lot of things also don't. So there's a lot of things when you start looking in the UV, finding hot things, and especially at sort of the lower luminosity end of what we were probing with these, sort of getting down to that 19th magnitude here. We're starting to see interesting things that just do not look like our strict star models already, and might be other types of populations of hot things, things that start showing sort of broad or narrow helium-2 emission, indicating either nebula or some sort of winds or disks around different types of stars in the lower end. So anyway, I'd love to talk to people more. I know have today of like, what are other things you can do to create stuff that have these hot UV things in sort of an intermediate luminosity range, because we're clearly finding other populations. Okay, so that was helium stars. I think I'm doing good. Let's talk a little bit about the common envelope thing. So this is another one of those very uncertain phases of stellar evolution, where again, sometimes when a star overfills its Roche lobe, it does so in a dynamically unstable way, and it will engulf the other star, and hopefully you come out the other end, or hopefully you don't if you study mergers, whatever you like. So either you will merge or you will successfully eject that envelope. We know that sometimes you have to successfully eject it, but this is obviously a very complicated physical process. And something we would love to actually understand is actually how you go from one to the other. All of the binary population synthesis models have to make assumptions for how, if you take this configuration, you enter a common envelope, what comes out the other side? Is it going to merge? Are you going to have a type binary? Where is that going to be? It's actually hard, this has changed a lot in recent years, so in the last 10 or 15 years, but historically, these simulations are hard, and actually modeling this all the way through, you have a variety of physical scales involved, and in general, they've had trouble reproducing observations. So this is just one showing as a function of mass ratio of the binary, what is the final separation after common envelope, and a lot of the stuff in red is simulations, and down here are a certain set of observations. And the main point here, again, there are new simulations from this, there are new observations, but they don't always reproduce the types of observations we see. So it would be nice. Also, an issue from the observational side is in terms of getting simulations to actually match, part of the issue is that these observations here, we mostly just have what is their state now? We can look at a system and say, okay, it's tight enough. These are the masses. It must be post-common envelope. But we don't usually have systems where you know what its configuration is now. And you also know like what were the masses and separations before the common envelope. That's what some of the modelers would really love. So they know they're trying to recreate the same thing. Part of the issue, there's a bunch of white dwarf main sequence binaries that we know are post-common envelope systems. The issue is that a lot of them are located in the field, and so it's hard to sort of backtrace to this is what it is now, but what was it before? And the fundamental issue is you think these underwent binary interactions, so it's hard to tell, did the white dwarf come from a more massive star that had interactions earlier in its evolution, or a lower mass system that was able to evolve further and grow its core later? It's hard to disentangle that for just binaries in the field. How we've been tackling this, particularly Stephanie Grondin is a PhD student at Toronto who is finishing this year. I think you'll actually be seeing her at a T-Talk in a month or so. She'll be visiting. But what she was doing was looking for post-common envelope binaries that are in star. Then you get an independent constraint on the age of those systems, and you can do something kind of like the equivalent of the initial final mass relationship for single white dwarfs. You can actually try to use the independent age constraint to backtrace what the system was before it underwent the common envelope. I'll show an example of how this will work in a sec. But the fundamental issue, the first thing we had to tackle was that there were only 2 white dwarf main sequence stars that are post-common envelopes that were known in stellar clusters, both in the Hyades. They were just like not examples of this. So this is what Stephanie was tackling now that we have things like Gaia and other things like that. So white dwarf main sequence stars have pretty distinctive colors because you literally have 2 stars that go like this. A really cold star, a really hot star. You can look for really distinctive colors or RGB shapes. So this is just showing you sort of both in a Gaia BPRP diagram. In the CMD, they come like in a very distinctive place, but also just their, colors. As you start to look, these are pan-stars colors. They really separate out. So what Stephanie did, she has sort of more of a background in dynamics, is she searched like 400 Milky Way clusters for things that she had confirmed were members of the cluster and tried to piece out now with more Gaia information, pan-star colors and other things, what is a new sample of these. She now has a sample of 55 high probability candidates where these things are cluster members and they look like white dwarf main sequence stars. There's a lot you can do with this study. And again, there were only 2. We're still confirming some of these, but there are only 2 that were known in clusters before. She has now this sample of 55 candidates. There's fun stuff you can do with it already. Like she sees evidence already of things where just based on their spatial locations, it looks like they're kicked out of the cluster a little bit. And this is not inconsistent with a very small kick, something like a few kilometers a second from either common envelope or something else. But she's working now to characterize these high probability systems. I'm going to show you a teaser of one of the events. This is our best case, but that's a good one to highlight. So this is just showing you it is a cluster member, both in position, proper motion, parallax, it's spot on with the cluster. And this is what the object looks like. So it's very clearly, you see evidence of here's a main sequence star and here's a white dwarf on top of it. It shows periodicity of about 0.3 days. We have a light curve now. Sorry, that's VPF data there. We have RVs for it now. It's a 0.6 day period system. It's definitely a post-common envelope one. So again, this would only be the 3rd confirmed case, and she has a full set of things she's analyzed. So what's cool about this is really what we're trying to do with this then, again, if we're trying to trace back the initial conditions of these things. So this is just highlighting sort of an example of what I mean by this. So here, these are stellar models that were made. They are with MESA, but they are sort of tailored ones made by Jason Norhaus at Rochester Institute of Technology. He does a lot of common envelope work. But what you're seeing here is stellar age. The black lines are the core mass. So think of it as the white dwarf mass with time. So that's this axis. And these again are for stars with ages between 1.8 to 2.8 solar masses initially. The pink lines are radius over time. But this is a different system that he and Phil Muirhead have been characterizing, where they measure the white dwarf mass to be something like 0.5 solar masses. That's what this line is here. So you can see that, you can take very different initial mass stars, and at some point, their core will be 0.5 solar masses at different points. So sort of, if this is the only information you had, you can't actually tell what initial mass star it came from, what was its radius at the time it interacted. It's actually hard to tell. But as soon as you start adding in the independent age constraints, like this is the age of the cluster that this one is in, you can add the cooling age and constrain it more, you can really piece down that there are only a few tracks that actually intersect with this. You can start to piece together the initial and final conditions, again, to try and help people link together what are the outcomes. Okay. Last 10 minutes. Let's talk a little bit more about supernovae. Swing back to the transient side. So what I'm showing you here is, again, if we're on our way to a binary neutron star merger, you had the first supernova. That was a little bit what I talked about before, but you eventually need to have a second supernova. And this is going to be a supernova that is pretty unique in that it has probably undergone its own phases of mass stripping. It'll be hydrogen 4 again, but you need it to be a pretty tight binary. And anyway, there are a lot of theoretical models here that suggest that the second supernova leading to a neutron supernova or a neutron star merger is expected to be ultra stripped. And what that means is it's kind of because it probably went through this additional phase of mass transfer here. You remove even more material So they're thought to probably have less than a solar mass of ejecta, in some cases down near only a few tenths of a solar mass of material thrown out in those explosions. And the biggest thing that means is that those are very fast evolving transients. If you have little material, they're going to evolve very quickly. So there have been a handful of cases. I'm showing you one of these. This is modeling of a 2005 supernova that was done by Thomas Forrest. There are now a handful of events. There were a few sort of in the mid sort of 2015 area, and now ZTF has added a handful more of these events, of things that we think are rapidly evolving and look probably like they're consistent with the second supernova leading to neutron star mergers. But I would say actually my take on this, maybe different people have different opinions, but overall there remain, like, we don't have too many of these examples still. And part of it is that they are very hard observationally to find. But we would love to understand them a little bit more, and we'd love to understand the intrinsic rate of those ultra-strict supernovae. But in order to do that, we need to both find more and then, I don't know, this is creating a little bit of a tangent, but I also think it is important in order to understand this phase in this diagram is you have to understand what is the full set of origin of things that are fast overall. Because we're not exactly sure what these objects should look like. We know there are a lot of fast transients now. Not all of them have been associated with these ultra-strict supernovae, but there are many types of things that evolve on short timescales, and we're trying to understand what leads to them. This is something, again, that Anna Ho, who was here at Caltech, has done a ton of work on of characterizing these populations now at short time scale, and they're almost certainly due to a wide variety of different types of explosions. But I think we're getting a firmer picture on it. The work that my group has been doing on this now, part of it is that I think I've gotten tireder, as I've aged a little bit, that I'm a child, but I've been trying to work a little more on late time observations of these fast transients. So things where I don't have to wake up in the middle of the night anymore, but that can still tell us important things about the physics of what's happening for transients that are happening on short time scales, but maybe then have longer lived emission that can give us important diagnostics. So I am pitching to you that late time observations are important. This is not new, like a lot of supernova people do this, but sometimes it's useful because at very late times you don't have as many sort of opacity effects, and you can directly trace the input power source. Also, the local environments can offer clues as to what type of explosion it is. Are you near a star cluster? Are you near other things? So one thing I'll highlight, this is not an ultra-strict supernovae, but it's an example of a fast transient where we did get late time observations that I think were really important for understanding the nature of the explosion. You may have heard about AT 2018 cow. It was nice because it had a nice cow-like name, so it was rolled off the tongue. But this was one of maybe the most luminous and fast evolving transients. It's the star in this diagram here. This was very well studied, had multi-wavelength data. There was presence of a long-lived sort of some kind of central engine creating extra emission. There was probably material around the star. There was a wide variety of hypotheses for this. Maybe it was a field explosion of a high mass star, the explosion of a low mass star. Maybe it was a tidal disruption around an intermediate mass black hole. All of these were proposed for this event. Many people in the room even studied this object. So what we did with this was, again, we were like, let's look at it years later when nobody else is doing it anymore, which wasn't quite true. But this was HST observations that were acquired at the location of this event years afterwards. So again, the idea behind this had been the transient will be gone. We'll just see if there's a stellar population around it. And maybe we can get an age constraint from that, something like that. That was the idea behind the data. But when you looked at the location, right at the exact location of the transient, there was this UV bright point source at the exact location where the transient was. Again, this was a very fast evolving transient, and this was here years later. So when you did repeated observations of this, this was led by Yu-Yang Chen, who's also a PhD student at University of Toronto. It was fading with time. It showed it was still transient. So this wasn't a star cluster that was just like located right at the position, but it was actually still a lingering emission from the transient itself that was there years after and was incredibly UV bright. This is just showing that again. But the best interpretation of this and sort of its slow evolution is that this is likely a remnant accretion disk that was created by the explosion, and you're still seeing it, and you're just seeing the UV bright emission. This was sort of the UV optical for it. It later was also found to have a very weak and soft X-ray component, which again matches with this picture of it really being a remnant disk that is left after the explosion. And again, it lasted, the data in this paper was from up to like 2 to 6 years. We've still been following it, is still there, it's very slowly evolving. We're almost, we're how many years later, but it's still there and present and just very slowly fading away. So it's an indication, again, it is some sort of transient where clearly accretion was important. The annoying thing is still you can either fit it with an intermediate mass black hole that's like doing sub-Eddington accretion or like a stellar mass black hole doing super Eddington. You can still fit it with both, but it still is sort of limiting the type of explosion models that fit. Okay, and so with that, I am not going to talk about neutron stars. Maybe we have reached the end. So I would use neutron star mergers to study things like nucleosynthesis and other stuff, but as I'm sure you've heard from many people, we are still waiting for a neutron star merger that we can follow up with all our active programs. So I'm happy to chat with people more about that and maybe why we haven't seen anything yet. I've already discussed this with a number of you, but mainly, there are a lot of constraints we're getting from gravitational wave information, and the lack of gravitational wave information is going to be really constraining, I think, for some of these binary evolution models and trying to understand recent rate constraints and news going forward in the future. But I will instead, this is not for this, and instead I will conclude. So thank you. The excess light. Yeah. Yeah, it's tough. It doesn't have to be crazy. Like we're not talking 1,000 solar radii. We're talking more like tens to 50 to maybe 100, like things in that range. And part of what matters though too, it's not only the radius, but the density distribution that you need as well. You don't want it to actually be too thin and inflated to that, because then your time scale for that first peak ends up really short, and it ends up being kind of like the 2Bs with only like 1/100th the solar mass of hydrogen. You get a really fast peak that's really bright, and it wouldn't blend in to the overall peak. So it both has to be the radius, but also the density distribution needs to not be too sparse. Otherwise, you get too fast a peak. It has to sort of be spread out. It also matters how your nickel, I'm sure Luke is maybe here, I saw it before. Like it matters how your nickel is distributed throughout, like how much mixing you have also affects if you get 2 peaks or if you get 2 peaks that overlap and look like 1 peak. Yeah. Some of hers didn't, but this is where the mixing came in. Yeah, exactly. So you do, it depends. Like these ones, right? Like these are some of her models. They rate like rise in, because mostly we see rise times that range from like 12 to 20 days or so. And they weren't so far off from some of ours. But it was true that some of hers rose much faster, and that's not consistent with what we see. Although there are 1 or 2 examples where you do see cases where you actually do see 2 peaks, including one. Right. Yeah, so in the context of like our actual candidates in the class. I think that mostly depends on, so the type of transient wind is talking about is you do have some supernova that are hydrogen poor, but actually pretty close by, you then run into clearly the hydrogen cell, indicating that either it has managed to stick around the binary system or it was ejected not that long ago. So I think it's mostly that you need to figure out the timing so that it ends up at that location. And that depends a little what was the mass loss mechanism. There are some examples of these stars where we look in our 2D spectra or in like narrowband image, and they do have, we see little confined nebula around it. So like we see the material that was ejected around some of these and can actually constrain the time scale of them. Now, again, some of these, we think these are core helium burning, so they're not too close. So you would need something that to explain those where it was much later when the material was ejected and it's still nearby. Yeah. Yeah. And so whether it makes sense. Yeah. Mm-hmm. Totally agree with you. Yeah. You can always do it. Yeah. Yeah, exactly. Let me go back and see. And I mean, that's always what the confusion has been, like whether these magnetars are what also people would call magnetars. Yeah. Yeah. Mhm. Yeah. And that makes sense to me. I'm trying to remember the paper by Rodriguez Nacar. Like I meant to look up. For some reason, they ended up favoring the magnetar case, and I don't remember why. But in my opinion, like, yeah, I don't know. I I don't think we can tell right now. There's a lot of then implications of either one of these in terms of we see this excess light and people have like different groups now have tried to measure like how much of the peak luminosity must be from something else, but that is going to have repercussions on all of our modeling. You know, because if we have to actually disentangle it, then it matters which of these two it's coming from. So it might mean that like we're going to need to revise a lot of that. Yeah, yes, I don't disagree with you. Yep. Yes. Yes. Yep. Yeah. So a couple. So we have a handful that do. I mean, I would say it's mixed too, because they're the ones that we have the good periods for. And then there are other ones in our candidates that we have X-rays for as well. And we need to like finish meshing those together and get orbits for the other ones. So we do have a handful. We also have new Chandra data that's coming in later this year for sort of the sets of them. Because there are a number where they have XMM coverage and even near zeta, but it's not quite deep enough. Because what we think for these is most of these are not filling their Roche lobes. So this is wind accretion. And so you need to be relatively tight in order to actually see the X-rays. Whereas, you know, we have good constraints. We don't see X-rays from this one that has a period of about a year, but you really wouldn't expect to unless it was a 40 solar mass black hole. I guess we do now that that exists, but it's not in this case. So for the wider ones, you don't expect to see it because it's just wind fed and they're pretty low mass off rate. It's mostly the tight ones. Yeah, exactly. Yeah. Yes, and we do for some of them. Yeah, and then some of the other ones are just it's just not quite deep enough. The predictions for like a neutron star companion are just below the maximum limit, so we're getting on reference. Something. It's nitrogen. Yeah, nitrogen 5. Yeah, and it's actually interesting. We went down, or I shouldn't say we, Ilva went down a rabbit hole of that. This is not a wind effect. It's actually an interesting photospheric effect. I'm not, I'm gonna box this. There's a few sentences of like where you see this in O stars too, where it comes from like what ionization state you're in, but it's actually not a wind feature, but you see it in O stars as well. So the idea is you do not have any other than one of ours, okay, I don't have it on it here. This star one, actually, if you really zoom in on this helium-2 feature, you see a little bit of infill coming up. Like that's the only wind feature we see in the optical. Whereas, yeah, those nitrogen-5 in emission, they are useful for constraining the temperature, but it's about what ionization that you're in and not actually a wind effect for those particular features. Yeah. Oh, hello. Yeah. It was a little post-fact. Not all of them are that good. But yeah. 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 Oh, we had one preliminary one, but I think there are better rates now from some of the VTF ones on what we think the rate for these ultra-swift. I don't know if you know it off the top of your head, Marcus, but yeah. There have been attempts to do this, yes. Yeah. 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 No, that's a good question. I don't know immediately, but I think that was. Yeah. No, exactly. And that's what I mean. Yeah. Yes, exactly. I was trying to be, it was a post facto way. No, exactly. It was a way to connect the fast trans. But yeah, no, we think that the ones that are actually these ultra stripped ones, maybe it's better in anodes. It's mostly these sort of the squares here. They're fast and faint. They're particularly faint usually, and they are ones that they actually end up looking mostly like normal supernova. Like you see the supernova features right from the get-go. They look like relatively normal-ish 1BC supernova. They're just very fast and quite faint because they have low exact masses. Are the ones that we usually associate with these. And those are the ones too that like DTF has published a number of cases of where they've sort of updated now of what we expected that sort of subgroup was saying. Okay, excellent.